So a vector is a quantity that gives you two pieces of information. One is a magnitude and the other is direction. So for example, if you tell somebody that you're driving, I don't know, 45 miles an hour, that's your speed. That's all it is. That's the only information that you get from there. If you tell somebody that you're driving 45 miles an hour west, now you have two pieces of information that came out of there. Your speed and your direction. Together, if you say 45 miles an hour west, together that is a vector quantity because it specifies direction and magnitude. Okay? So that's the difference between a vector and a scalar. If you guys are in physics, you've seen this. When you get to physics, you will also see it. So that's what a vector is. It's a quantity that has both magnitude and direction. An example is velocity or force. Force is never just 5 newtons. It's 5 newtons in a certain direction. Okay? So that's a vector quantity. A quantity which has only a magnitude and no direction is called a scalar. And do you remember, where have we seen that word scalar before in this class? That's a scalene triangle. In this specific class, do you remember in 6?
It's matrices.
In chapter 6, when we multiplied a matrix by like 3, we called that scalar multiplication because just the 3 on its own, you know, without it being part of a matrix, is a scalar. So here, when we're talking about vectors, a scalar is only has a magnitude. So I'm driving 60 miles an hour, period. That's it. Okay. So to distinguish, you can say that the velocity of a certain object is 6 meters per second east, whereas the speed is just 6 meters per second. Okay? All right, so let's try to classify some of these. You have a ball is thrown northwest at 60 meters per second. Is that a vector or a scalar quantity? That's a vector quantity because it's got magnitude and direction. A tennis ball served at 110 miles an hour? Scalar. A sprinter running 100 meters north? Vector. Okay, so now that we know what they are, what a vector quantity is, let's talk about how we represent vectors. Okay, so vectors are usually represented by an arrow. It's called an arrow diagram, or it's called a directed line segment. So take a look at this. This is a vector. All right, so notice this vector has an end point at one of the ends, and it's got an arrow on one of the other ends. So if you want to compare, you know, like in geometry, when you talked about rays, right? That's how they look. Now, A is the initial point. This is where the vector originated. It's also called a tail. I like using initial point better because it's clearer. B then is the terminal point, also called the tip or the head. Again, I like initial point and terminal point. It makes it so much simpler for us. Back in the day, it was always like head and tail. It gets confusing because that is kind of ambiguous. Okay, so initial point has a name with a capital letter. All right, so that's, in this case, it's A. The terminal point is also named with a capital letter. In this case, it's B. So you have to give the vector the 2 points, the initial and the final, both in capital letters. And so this vector will be called vector AB, not BA, because that will go in a different direction. So vector AB. You could also give it a lowercase letter name, one letter. So vector A, vector B, vector C. It has nothing to do with the initial and final points. So if the initial and terminal points were A and B, you could call it little d. It doesn't matter, okay? Or little v, okay? It really doesn't matter. Okay? Now, this is how we denote vectors. When we're writing it by hand, it's capital A, capital B, and then the top, this is a new symbol. It's a one-sided arrow like that. Okay? Not like in geometry, not like this. Okay? Or you could do vector A like that. Either or. In books, most of the time, they use this notation, and that's how I usually do it on my tests and stuff too, is just a boldened lowercase name. Okay? All right, so that's how we name. Right, you can't do it on, like when you're writing by hand. So when I write by hand, it's one of these, but in the, like when I print, it's that one. Okay? All right, so let's now put it on the coordinate axes. So in math, you know, like whatever we have, we always like put it on the x and y axis, and then we could just do things with it, right? So when a vector is in standard position, remember we talked about what angles were in standard position? A vector in standard position, has its initial point at the origin. That's it. So the initial point A is right there at the origin. Now, the direction of the vector is the angle between the vector and a horizontal line. Okay? So, in this case, I have my vector here, and look at this. This is the x-axis is a horizontal line at the initial point. There is an angle of 35 degrees between that horizontal line and the actual vector. That's the direction. Okay? All right. If you have a vector, you know, out in space, and you want to specify its direction, you yourself, you draw a horizontal line, and then the angle is the direction. Okay? Now, that's the direction. The magnitude is the length of the line segment. So they're usually scaled. All right? And the magnitude is denoted by absolute value of A. So that's not absolute value, that's magnitude. Okay, so starting right about like middle school and then through Algebra 1, you know, student, you know, that's always absolute value. Okay? Later on, when we get into like higher level, real, actual, like real life math, the absolute value, those bars always mean like a magnitude or the actual value and so on. Okay, so in this one, all right, in this vector, if you were to take a ruler and measure it, this turns out to be 2.6 centimeters. Okay? Now, no, but you need to know this concept. So if you were told that 1 centimeter represents 5 feet per second, that vector, right, if each centimeter is 5 feet and this is 2.6 centimeters, then the magnitude of that vector is 5 times 2.6, which is 13 feet per second. Okay? So, okay, so you can see that these are very, very useful in describing where something is located, right? In fact, in aeronautics, like in like when you talk about like ships or planes and so on, vectors are very useful in giving coordinates of where something is. All right, so let's talk about bearing for a minute. This is one way vectors are represented. Okay. So when we talk about bearing, that's another way of expressing direction. Now, there is quadrant bearing and true bearing, okay? Quadrant bearing is a directional measure between 0 and 90, east or west of the north-south line. Okay, what the heck does that mean? So, look at this one here. All right? The quadrant bearing is this phi right here, that angle on the bottom, this one. Okay, so if from here to here it's 145, to specify in terms of quadrant bearing, the actual angle can only be between 0 and 90. So if that whole thing is 145, how much is this? 35. Okay, so how do you get to that angle? You have to go 35 degrees. You have to go 35 degrees east from south, right? So the way you write it is S35E. Because again, how do you get there? You have to go 35 degrees east of south. So what if you said 35 degrees east of north? Where would that point? Upwards. Okay, so do you see how like there's only one way for you guys to say that? Okay?
You say south of east. Like however many degrees south of east.
Oh, because quadrant bearing is, it's agreed upon that it has to be from the north-south line, right? That's how it's defined here, right? Okay, so this
you can never do it more than 90.
Correct.
Okay.
This is how they do it for, like, if you watch war movies and like there's a submarine and it's being attacked, like this is how in like the Navy, like in aeronautics, that's how they specify
It's like relative
quantities. Reference angles, you mean? Sort of, yeah, sort of. Okay, now, and then there is true bearing. In some fields they do that. I used to have a student who was like adamant into going into the Navy, and then when I started talking about this stuff, oh my gosh, like their eyes lit up, and then I was like, oh my god, this is like exactly what whatever. So that they use it in like I said, in aeronautics. Okay, so true bearing is where the angle is measured clockwise from north, always, just from north. Okay, and it always has to have 3 digits. So a direction measuring 25 degrees from north is expressed as 0.25. Okay, so if this is the north, okay, and if you go like 25 degrees from there, you give it, 0.25, all right? And it could go up to 360. Okay, you could go up to 360. Okay, so that much about bearing. Now let's talk some more about vectors. Okay, so here are some vectors. I just basically took a couple of vectors and just threw them up in the air, and that's how they landed. Okay, you've got vectors A through F. Okay, what are parallel vectors? Parallel vectors have the same or the opposite direction, but not necessarily the same magnitude. All right, so what are some parallel vectors here? They basically have like similar angles. Yeah. C and E look like they're parallel. Any others? A, B, and F, right? So the way we're going to do it is A is parallel to B, to C, to E, to F. All right, equivalent vectors. Same magnitude and direction. It's like if you cloned one, but, set it off from each other. So what do you think? Equivalent vectors? Any equivalent vectors here? Not C and E. A and C. A and C, because they have to have the same magnitude and the same direction. So that's A and C. It's A equals C. That's an equal sign. There's a dot that persistently didn't want to go away. Okay? Opposite vectors have the same magnitude but opposite directions. So in this case, E and C, or E and A. Okay? So they have the same magnitude but opposite direction. No, because they're opposite. So that's what I was going to say next. If you have vector E, it points in the opposite direction as vector A, correct? Okay, in the world of vectors, direction is specified by the symbol, negative or positive in front. So the sign, SIGN, gives direction. So if E is the opposite of vector A, then we say it's got the negative direction, so it's negative of vector A. Okay? So here, negative represents direction. All right. So in physics, In the real world, we go like 60 miles an hour. In physics, if you go negative 60 miles an hour, where are you going? In the opposite direction. You're going backwards. You're going opposite to where positive is. Okay? All right. Resultant vectors. Okay. Resultant vectors are what you get when two or more vectors are added. Okay? When you add numbers, what you get is a sum. When you add vectors, what you get is a resultant. We don't say that's the sum. We say that's the resultant vector. Okay? Now, there are two methods to find resultant vectors. It's the triangle method and the parallelogram method. I always prefer the triangle method. Coming from a physics point of view, coming, from like the real world application, it just occurs more frequently that, that's more useful. Okay, so here's how we add vectors. All right? To find the resultant of A and B. So look, I have vector A and I have vector B. I'm going to add A plus B. Okay? But adding vectors looks very different than adding numbers. So the way you do it is this. You take vector A, okay? And you just draw vector A somewhere. Now, remember, one is the, okay, which is the tip and which is the tail?
The one that without.
Huh?
The tail gets the arrow.
Okay, so you're guessing, right? Now, if I said, okay, now if I said which is the initial, which is the terminal point, is that easier? Right? There is no confusion. So I'm not going to use tip and tail. I'm going to use initial and terminal. Okay? So you do this. Now, this is the terminal. This is where the terminal point of A is. Okay? You take B and you want to put the initial of B at the terminal of A. All right? So like that. Okay? The way I like to say it is, this one ends, it's like, what do you call it when like they do like a relay race? You know how like when you, like where one person ends, another one comes and just picks up? Right. So this vector ends here. The other one picks up. Okay, now you drew the two vectors, final in terminal tip to terminal to initial. Then what you want to do is you want to connect the very beginning, okay, the initial point of the first one with the very, very end, the terminal of the second one. Okay, so initial of the first, terminal of the second. Okay? And the way I tell my students to look at this is, imagine if this was somebody's route, okay, and then somebody stopped there, and then somebody picked up the route and went that way. Now what you want to do is a bird's eye view from beginning to end of the story. From beginning to end. Where did they start? Where did they end? Okay? All right, and then that green one is the sum. It's the resultant. So it's kind of weird. So you know with numbers, if you have a 3 and a 5, you add them, what do you get? 8. If you have this and you have this, you add them, that's what you get. Okay? Yeah.
What if A and B are going like in the same direction?
Then they add to each other. So we're going to do a couple like that. Good. Yeah, we're going to do a couple like that. So let's draw the resultant of each pair of vectors here.
Which one do you do first?
Huh?
The one on the left or the one on the right?
Okay. So it really doesn't matter, but I always like to go in like in alphabetical order. So here it says state the magnitude and the direction relative to the horizontal. I'm gonna do like the light version of that. Okay. So here's vector V. And look, this is vector V right there, right? Okay. And you know what I'm going to do? I'm just sort of like going to reproduce that here. Oh, I'm going to reproduce that here. Okay. And then here is W. I'm going to reproduce that there. So it's important that where one ends, the other one begins. And how would you draw the resultant? From the very beginning to the very end. And hang on, and you have to put the arrow in the correct position. Okay? We started here and we ended there. I used to make students like measure, and then add, and then measure, and blah, blah, blah. I'm not going to make you do that. However, you should be able to put initial to terminal and draw the resultant in the correct direction. Because later on in the word problems, this is going to be like super helpful. Okay? Question? Okay. Yes, thank you. Thank you. I forgot to say that. Okay, this one here, right? This one here is your resultant vector. You always have to label it as R. Okay? That's just an R with a
You don't write like the
R vector. Huh?
You don't write W, how do you scroll up?
Yeah, it's the same. It's the same. A plus B, it's the same as the resultant. Yeah, just tell me in some way that that's the resultant. Okay, take a look here. I've got A and I've got negative A. I'm going to draw the blue A. Yeah.
When you wrote the R, you wrote the symbol for vector. Do you have to do it or can you just say R?
No, vector. It's got to be vector.
Even if we put R weight
Even if you did. Huh?
we put R weight next to the vector.
Yes. Okay.
R, is that R?
That's an R and the arrow.
Okay. If we do V plus W, is that wrong?
It's not wrong if you do V plus W. Make sure, though, that you put the vectors symbols. Okay? All right. You will develop like your own preference by the time we finish this chapter. Okay, take a look at this one here. You have vector A here and then negative A here. Okay? So how is that going to look right now? So negative A, so this is the terminal of this. I'm going to put the beginning of vector A here, of vector negative A here, and it's going to go this way. Okay? And where's the resultant? Where was the very, very beginning of the story? Here. Where is the very, very end of the story? There. How much net have you walked? 0. So the resultant here is 0. Yeah. I'm never going to ask you this. This is too simple of a question for me to waste a question on. But you need to know that, so if you have vector A plus negative A, the sum is 0. All right. You know what? Here, let me do another example. Oops. Let me do another example. So suppose this is vector V, and this is vector W. All right. What would V plus W look like? Yeah. 2 arrows. Okay, so V is here. Now, I'm going to put the initial point of V at the terminal point of W. So I'm just going to continue and points that way. And now the resultant goes from the very beginning to the very end. So that is the resultant. Okay?
It's like it hasn't changed, like the direction's exactly in the
Yeah. Okay? All right. Multiplying a vector by a scalar. If I have this as, vector A, and now if I multiply this by 3, right? What I do is I multiply the magnitude by 3. So this was vector A, and then I multiply it by 3, and now it's 3 times longer. Okay? All right, so take a look at what we're going to do here. All right, here's vector x, here's vector y. I want to draw 3x minus 3/4 w. Okay, I'm sorry, I keep saying w, it's y. What's 3x going to look like? 3 times the length of this, so 1, 2, 3, in the same direction, right? That doesn't change. What's negative 3/4 y going to look like? Well, if it's negative, it's got to change direction. Okay? Changes direction. Yeah. And it's 3/4 of the length. 3/4 of the length is about yay big, right? So that's negative 3/4 y. Okay? So now where am I going to put that? This vector starts here. Where it ends, the other one will pick up and go this way. So where it ends, the other one, this 3/4 will pick up and go this way. And now, my resultant is going to go from the very beginning of the story to the very end of the story this way. Okay? So this is the resultant, which is also 3x minus 3/4 y. No, because where did this whole thing start? Here, right? And where did it end? There. So you have to give that idea that it started there and it ended here. If the arrow goes backwards, then you're saying we started here and we ended there. Right, but like it would have to have one. Yeah. Okay. All right, let's talk about components. This is, until now, we really haven't done anything with vectors. Believe it or not, we really haven't done anything. We're just like getting you introduced to terminology. Okay, now vector components is when it starts. Okay. So look at this vector r. How did it get created? It was created when we added the red and the blue vectors. Okay? So the green came from 2 other vectors. All right? Which means if the 3x, if the red and the blue added to create this green vector, then the red and the blue are the components of this green. All right? So vectors which add to create an R are called the components of R. All right? When working with vectors, we always want to break them down into the components from which it came. Okay, so now take a look at this. Suppose I've got a vector like that, and I want to break it down into 2 other vectors which add to make that. How can I do that? How can I break it down? Look, I could do 1 vector there and 1 vector there. Okay? How else could I break that down? Same vector. How else can I break it down? I could do 1 vector there and another vector there. In both cases, red and blue are the components. Red and blue are the components. Somebody else might come along and they'll say, oh, you want me to create 2 vectors that add to that? Well, here's one and here's another one. Okay? What did this person do? They created 2 components which happen to be perpendicular to each other. One is horizontal, one is vertical. So you can break a component, you can break a vector into any components, but it's most useful to do this. All right, because that's x-axis, y-axis. All right. So what do we call these? We call these rectangular components, horizontal and vertical. The red is horizontal and the blue is vertical. Huh?
What's rectangular? Oh, is that just?
Oh, yeah. Rectangular just means that like it's horizontal and vertical. Okay. All right. So let's talk
They're
about.
both rectangular. Even though one's horizontal, one's vertical, but they're both rectangular.
Right. When we say break it down into rectangular components, we mean into horizontal and vertical components. All right? Okay. While digging into his garden, Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees with the ground. Okay? Draw a diagram that shows the resolution of the force that Will exerts into its rectangular components. Okay, so let's draw a diagram here. Okay, so this guy's digging into his garden. So he's got the shovel and he's digging down. And this makes an angle of 70 degrees with the ground, right? So here's the ground. Let's make it. Here's the ground. All right, so where is this shovel? This is the shovel. Now, which way will this arrow point? Which way is the force going? Is it going downwards into the ground? Right. Okay? So that's his force. And we say this is a force vector. And its magnitude is 630 newtons. Like this. Yeah.
Why is it that angle? Why can't it be like exact same angle but reflected?
Same. Doesn't make a difference.
It doesn't.
No, it doesn't. So now it says that it's got a force of 630 newtons at an angle of 70 degrees with the ground. So where's the angle? Where are we going to put it? Left or right? Well, it looks like this one. I made it 70 degrees. So there. Okay? Yeah.
For this would be actually like draw a diagram or just like what you did?
This is good enough. This is even more than, yeah, you don't need to be an artist here. Don't like, I don't do that. I can't even. Okay? Now, it says draw a diagram, okay, that shows the resolution. Okay, what's that word resolution? Okay, so when it says that shows the resolution, it means broken into components. I was talking about partial fraction decomposition in calculus class today, and they were all like, nope, we've never seen that before. And I'm just like, all that time and energy and like breath I spent. Anywho, okay. So we're going to resolve it into its rectangular components, right? So how does that look into its rectangular components? All right, now this is the tricky part, okay? Okay, so we start from the beginning here, all right? And we're going to make two vectors that give the same route as that. So basically, it's what are some ways that you could go from the beginning to the end of this? Well, I'm going to go down, and then I'm going to go across. Okay, now, placement of arrows is super important. If I trace the beginning to end of the actual vector, I start here and I end there. Now, if I take the other route of the rectangular components, I need to start and end in the same position. Got it? So no matter which way I go, I'm going to end in the same position. So when I grade this, I look for arrows placed correctly. Okay? Can you draw it this way? Boom, boom, yes. Okay? Yeah, just make sure that, yes, we're going to label now. We're going to label now. Okay, now we're going to label. This vertical, we usually call it Y vector. And guess what this is called, guys? X vector. Okay? So now it says to find so again, just to repeat, it could also be drawn this way. Okay? All right. Find the magnitudes of the horizontal and vertical components of the force. So now we need to find the magnitudes of the horizontal and vertical components. So we have to find the magnitude of X and the magnitude of Y. Okay? All right, let's do this. Now, what I'm going to do is I'm just going to draw that bigger here. So this is Y, and this is X, and that's F. Okay, and F is 630 newtons, and there is an angle of 70 here. Okay, how can I relate X to what I have? Cosine. Cosine, it's back. This is where it comes back, and then it's going to come back in chapter 9 as well. It's going to come back. It's going to come back a little more heavily in chapter 9. Polar coordinates, but let's leave that be. I know. Okay. So, sine of 70 degrees is equal to X, no it's not. Cosine of 70 degrees is equal to X over 630. Okay? That's all fine, but what's X equal to then? X is equal to 630 cosine 70. Okay, and when we put that in the calculator, what do we get? Make sure your calculators are in degree mode. Tell me what you get. Okay, 215.5. This is still a component of the force, so it's got the same units as the force. Okay, now the sine of 70 degrees, I've never heard that joke before when I'm teaching about force. The sine of 70 degrees is what?
I had to make the joke.
Y over what? Y over 630. So that means Y, component of Y, is equal to 630 sine of 70. And how much is that? Newtons. Okay, so that's the vertical component of the force, and that's the horizontal component of the force. Now, we said before that X and Y add in quotes to make the vector F. Now, if you add the numerical value of the magnitudes of X and Y, do they add to 630? No, they will not. Okay? They will not, because vector addition is not numerical addition. And we'll see later how they actually add to each other. Okay? I mean, you could for fun, but we're never going to do Pythagorean. We're never going to do Pythagorean theorem here. Okay? So, in fact, here we wrote this cosine equals X over 630, sine equals Y over 630. This is usually not the way we write it. More and more, as we progress through this chapter, and even though it's only 3 lessons, but believe me, you know, more and more, we're going to use this version of it. It may seem like, you know, potato to you, tomato to you, but this is the way we do it in the vector world, okay? Because if you've seen this stuff in physics or in the real world, this is how it works, all right? So the X component, here's how you can see it. The X component is here, okay? The horizontal component is here. This is adjacent, and this is why. This is why. When we do chapter 4 and 5, I have a specific set of words and specific language, because this is where we use that now, okay? This is the adjacent side, right? That's the cosine. So when you're looking for this component, it's gonna be the vector times the cosine of the angle because it's the adjacent. And remember how the vertical was always the sine? Do you remember how many, right? Like how much like tears and sweat and just to like ingrain that into you. The vertical was always the sine. So the vertical is always going to be the vector times the sine of the angle. All right? This is why I use that language in chapter 4. Yeah.
So like, people like write it.
By the way, it's the character in one of the Despicable Me movies.
It's Victor.
That's Vector.
Oh, yeah, no, you're right. That's
I am right. I know my math characters. It's the guy. It's the villain. He's the villain. Huh? Yeah, the villain in Despicable. There's lots. Okay, this one. A player kicks a soccer ball so that it leaves with an S. It leaves the ground with a velocity of 44 feet per second at an angle of 33 degrees with the ground. Now, again, draw a diagram that shows the resolution of this force into its rectangular components. This is not a diagram. This is a picture. It's useless to us. Draw a diagram that shows the resolution of this force. Okay, so, okay. So he kicks the soccer ball with a velocity of 44 feet per second. This is your vector. All right? With an angle of 33 degrees with the ground. So if this is the ground, no, velocity is a vector quantity. Speed is not. So he kicks upwards, right? You're not gonna put the arrow here because that's not the direction that he's kicking. You're gonna put the arrow on the top. So that's V, and that's 44 feet per second. And it's got an angle of 33 degrees with the ground. So that's my vector. And then if I want to show the resolution of the force into the rectangular components, then here I've got the X component, and here I've got the Y component. Where is it?
How do we know which is which? Just which one comes first? Is that?
I usually call the horizontal X.
Isn't it, isn't it, initial point to terminal point?
Huh?
Well, when we're adding vectors, is it not in, my bad, yeah.
Okay, so here's how I do it. Here's how I do it.
Okay.
You want to go from the beginning to the end of the purple vector. You want to create your other vectors so that if you go, if you follow, you go from beginning to end of the purple vector. Okay? I have so much to say about vectors. I feel like I can't get it all in. Okay, so this is X and this is Y. So that's the diagram. Okay, now find the magnitude of the horizontal and vertical components. So X component, this is the horizontal cosine, all right? It's the adjacent, it's the cosine. So it's going to be the vector 44 cosine times the angle.
Would you not put the...
Yeah, you do. So the magnitude is how much?
36.9.
What are the units?
feet per second.
Feet per second. Okay, the Y component is... No, that's the vertical. That's the opposite. So it's got to have a sine. So you always start with the original vector, sine of the angle. And that's going to be
23.24. Well, it's 23.96.
okay, so 24.0 feet per second.
Would you have to if we get a value, if we got 50 for either X or Y for the magnitude, we would have to figure out something else because like that doesn't make sense. You know, it's like
Right.
triangles.
Right. So these components are going to have a value less than the original vector. Okay? So now what does this all mean? When this person kicks, right? You see how the soccer ball goes in this direction. It doesn't go straight up and it doesn't go straight across. That means, how does it go there? That means at each point it's going up a little bit and it's going over a little bit, up a little bit, over a little bit. Right, up and over. So you give it, when you give it an angled velocity, right, at each step it's going up and over a little bit, up and over, not purely up, not purely over. Now, you see here, the x component, this is the magnitude of the velocity. So how much velocity does it have in the x direction and the y direction? You see that the x component is a little bit bigger. So this is going to go more across than up. You see that? So, you know, like these things, you know, mean something. Okay.
No, I'm not talking about that. When they're like, when they're studying something, like,
A force, we did the soccer ball. Let's do another one. Another classic problem is an airplane. So another classic one is an airplane with some wind. So you know that if there is wind, the wind changes the direction of the airplane a little bit. So the pilot has to, you know, like adjust the angle or whatever in order to, you know, counteract the force of the wind. So an airplane is flying 40 degrees north of east with an airspeed of 310 knots in still air. Okay? It encounters a 78 knot tailwind acting in the direction of 145 degrees north of east. Because of the wind, the airplane acquires new ground speed and direction. What are they? Okay, so I actually am just going to draw this right now. So let's do the airplane for now. It's flying 40 degrees north of east. Okay, east is that way. North of east, right? So if east is this way, then 40 degrees north of east looks like that. Okay? Oh, you know what? I'm actually going to draw that on the bottom a little bit. Hang on. Let me do this whole thing. So that's the eastern, that's the direction to the east. 40 degrees, 310 knots, 40 degrees east. North of east. So that's how that looks. Now I'm going to call this vector P for plane. Now, it encounters a 78 knot wind acting in the direction 145 degrees north of east. So, if this is east again, 145 degrees is where? Like in that direction, right? Do you see that? If this is east this way, 145 degrees north of east is that way, 145 degrees. Is that right?
But how is the purple north of east also?
Yeah, the purple, okay, because the purple is only 40 degrees north of east. Now, if you were to go 40, 90, 145, then you're going that way. Okay? Now, that vector is acting on this vector. So this is vector A and that's vector B. So where are we going to draw vector B? At the beginning or end of this? At the end of it, here. So here is how we do it in order to be most efficient. At the end of it here, if this is the direction east, 145 degrees is going that way. Okay? In the beginning, it's very confusing. It's going that way. Now, how much is it? It's 78 knots. So I kind of want to scale it a little bit. If this is 310 and that's 78, that's about like a quarter of it, right? So it's going to be much smaller is what I'm saying, like this. I'm going to call that vector W. Yeah.
How is that a tailwind? Is that like what you're
It's a tailwind because it's not tail. It's like drag, right? Because it's going in the opposite direction, so it makes it drag. You know what I mean? So that's a different, yeah. So P is equal to 310 knots. And W is that. Okay, so now what are we going to do? Now what's the resultant? It goes from here to here.
Wait, is W not equal to 79, 78 knots?
It is. I just didn't write it because of time. So now, do you see how the wind is pushing the airplane back a little bit? It's holding it back. It's doing two things. If the airplane was going in this direction, the wind is making it tilt up a little bit. So what does the pilot have to do? Counteract that so that, it stays level. And then what will happen to the speed? Do you see how the green is a little bit smaller than the purple? The speed is going to slow down a little bit. Okay? So we're not going to solve the specifics of this because I just put this over here for diagram purposes. But go ahead and do this one for tomorrow.
Friday.
Oh, hang on, for Friday. A lot of them are things like this where you just have to draw vectors. Okay?
Down.
Thank you,